Hi, so today I'll be discussing NatPy, which is a simple package that we've made for dealing with natural units in your Python code. NatPy leverages astropy and NumPy, and you can get it through pip. So to start with, has anyone ever wanted to convert MeV per femtometer cubed to, say, pascals? Well, now you can. Just simply define a unitful parameter after importing NatPy, and we can do that like so. And then we can just call NatPy's convert method, telling NatPy exactly what units we wish to convert our expression to. And there we go. So in high energy physics, this is not anything new, but of course, the standard convention is to set h bar equal to c equal to epsilon not equal to 1. And what this does is implicitly rescale our physical quantities, okay? And so the fine structure constant becomes 1 on 137, the electric charge becomes scalar, mass, momentum, energy, length, cross-section, time are all measured in various powers of GeV. And to recover these SI quantities, we have to insert certain factors of h bar or h bar c or h bar c squared, etc., or c squared. And so that's where NatPy comes in. So NatPy quantities are astropy objects, and we can easily access all of astropy's constants easily, like so: speed of light, h bar, the electric charge. And so now where NatPy comes in is, if say I wanted to convert the electric charge to its natural unit form, I would again just call the convert method, specifying that I want the new dimension to be unitless, which we've called 1 or nat.1 for short. And as you can see here, we just recover what we saw before up here. Okay. And so, converting single quantities is easy, and that's all well and good. But how does a real world example look? A physics analysis, in a real world scenario. And so I've just cooked up something here. So consider calculating the average decay length of some new physics. Okay, so we've got some equations. The average decay length, goes with some Lorentz factors, and it goes as 1 on the decay width. The decay width is given down here. I've got some heavy new physics chi2 decaying to some lighter particle chi1 and some leptons. Okay, so just a typical inelastic dark matter type scenario, for example. This process is mediated by some heavy vector MA prime with mass MA prime. But at the end of the day, there are some equations. We have some quantities, they're all unitful. And this is all well and good. So, this is all in natural units, fine. But let's say we're an experimentalist and we want to, say, calculate some sensitivities for some future detector or something like this. We may want this, we may want to calculate this decay length in meters or centimeters, kilometers, for doing non-baseline stuff. And, you might be able to look at this and just see what you have to do to convert everything from natural units. But, for things that are more complicated, it might not be so simple. But, just as a kind of hello world example, we'll go through and calculate everything here. So I've just defined a bunch of my model inputs here. Okay, so again, I'm just going to define my masses in natural units. So this, the mass of this chi1 is going to be 10 GeV. For reasons, the mass of the vector is 3 times that, and I specify this mass splitting delta, the mass of this chi2, and the other model parameters epsilon, this alpha dark. This alpha EM is the fine structure constant, which we'll use NatPy as just constant intrinsics for this. Okay, so this is all in natural units, and so everything's easy now. I can just basically code this up verbatim, and so that's what I've done here. I've calculated the decay width, which is a function of these model parameters. You can see my Lorentz factors, beta, and the boost factor. The boost factor, for the record, being calculated in natural units because I can. And eventually I've got my decay length here, and so I can do that. Now, this is going to be a function of the decaying particles 3 momentum, which let's say is 7 GeV, just as an exercise. And if I execute that, I get an answer as I expected to be in inverse GeV, because my decay length goes as 1 on gamma. And gamma is, as everyone knows, is in natural units at GeV. But, this might be good for most people, right? You might see that, okay, inverse GeV, I know what I have to do. I can go back up here. I see that it's a length that I want. And so I just insert the relative, required factor of h bar c, and I'm good. But we've got NatPy, so we'll just use that. And we can, again, call this convert method, telling NatPy that we want our answer in meters. And there we go. And so the point is, as long as intrinsic natural unit consistency is achieved in our code, we can always convert the final result, or anything in between, actually, to whatever units we want, as long as it's all consistent within our specified units. And so to demonstrate this, I'm going to do something spicy. I'm going to say, hey, let's in fact define my mass of this lighter particle in kilograms. I don't know why you'd want to do that, but let's just say we do. Okay, so a 10 GeV particle is about 10 to the negative 26 kilograms. What happens if we rerun this guy? Well, I recalculate things, and okay, we get a slightly funky answer. We've got this prefactor here, which is quite large, and NatPy has just carried through all of the units, and we've got something in GeV to the power 4 on kilograms to the 5. Okay, not very useful. But again, we can just use NatPy, tell it we want everything in meters, and we get exactly the same answer. This is a very simple example, but as you can imagine, if things are very much more complicated, it can very quickly start to become the case where we start dropping factors of h bar or c, or just even scale factors, kilograms to grams, or GeV to keV. NatPy handles everything as long as we specify the units to begin with, and our equations make dimensionful sense. Well, that's not all. By default, NatPy ships with a bunch of unit conventions. The user can specify their own. By default, we have h bar equals c equals epsilon naught equals 1, but we can set our active units to be Planck units. And this little example here lets us recover the Planck length. And so what I've just done is convert 1 to meters, right, which in Planck units just gives us the Planck length. So that's it. That's basically all I wanted to get through. And I'm not sure if I have gone over time or if I'm hearing the cue.
I was just going to give you a warning, so you're perfect.
Yep. Okay. Good for time?
Yep, good. You have 3 questions. If you could share the Slido in a tab in your browser, make it big and read the question.
Make it big and read the question. Okay. Okay.
Control mouse wheel.
Yeah. My computer doesn't want to do this. I'm sorry. I'll just read them perhaps. Okay. So the first question here is from Jim. If any quantities in natural units are extreme floating point values, exponents abound around plus or minus 100, do you see numerical precision issues? Potentially. I haven't broken it yet. Everything I've used NatPy for has so far worked well. Again, I don't use anything with these large components, but again, I can't really tell you because I haven't done the testing. I don't see it happening because I haven't experienced this myself. Anonymous says, can these units be made to work inside NumPy arrays, or is it limited to individual values? Yes, so they can work in NumPy arrays. Where do you get your constants from? Any chance you can sync with HEP units? I don't know about syncing with HEP units, but we get them from astropy.